In this lesson, we're going to look at what the second derivative of a function tells us about the description for graph behavior. But let's go ahead and get warmed up with what did the first derivative tell us about a function. We learned in the previous lesson that if the first derivative is positive, that we would know that f, the original function, is increasing. Similarly, we talked about how if the first derivative was negative, that we would know that f is decreasing. A new piece of vocabulary that we learned with the first derivative test was critical number. A critical number is a place where the first derivative is equal to 0 or undefined. And why these were important to us was these were the candidates for relative extrema. Well, what would a second derivative tell us about an original function? The second derivative test describes the concavity of a function at a certain x value. So for instance, if the second derivative is positive, then the function is concave up. So if I wanted to draw a sketch of a function that's always concave up, that could even just be like a simple parabola. So for this particular function, the second derivative is always positive. Okay, similarly, when the second derivative is negative, the function is always concave down. And there are many functions where they possibly have a change in concavity. So what if we ran into a situation where the second derivative of a function was equal to 0 or undefined? So I guess if it's neither positive or negative, I would say it has, it's neither concave up or concave down. What that could mean to us is it could mean that it's a place where the function changes concavity. So for instance, we'll look at some different examples of this in just a second. A linear function would be an example of a function whose second derivative is equal to 0, and if that makes sense, a linear function doesn't have any concavity, so I don't have any, I wouldn't expect my second derivative to be positive or negative there. But let's check about how the function could have a change in concavity. If we had something like a polynomial function, a place where the second derivative would be equal to 0 would be at this point right here, because somewhere around that region the function's changing from concave down to concave up. So at this particular instance, the original function's neither concave up or concave down. Well, a place where the second derivative might be undefined may also have something like a cusp for the function. So if the original function has a cusp, at this particular point here, both the first derivative and the second derivative are undefined. And notice that the function's concave down here and concave down here, so there isn't a change in concavity here, but the function is neither concave up or concave down at this point. The third behavior I'd like to look at is oftentimes vertical asymptotes can be a place where the function changes concavity. We have to be a little bit careful with this description because along this vertical asymptote, this point's not actually in the domain of the function, but it does show up as a place where the second derivative is undefined. Notice that the function's concave down here and concave up here. So when we did the first derivative test, we talked about how the values where the first derivative were equal to 0 or undefined were called critical numbers. What other behavior occurred at critical numbers, or what is a more specific label that these points could have? So sometimes they were mins, maxes, or neither. Those were our options. Second derivatives also have something that's similar to critical numbers. The values at which the second derivative is 0 or undefined are called possible inflection points. I usually abbreviate these as PIPs for short, possible inflection points. Some pips will actually be an inflection point for the function. An inflection point is a point that's in the domain of the function where the function changes concavity. But not all pips are actual inflection points. If we had looked back here, the function didn't change concavity. It's concave down, so this wouldn't actually be an inflection point, but this would have showed up as a pip. Similarly with the vertical asymptote, even though there was a change in concavity on either side of this value at the vertical at this particular x value, this is not in the domain of the original function, so it'll show up as a pip, but it's not an actual inflection point. This is the only one out of these that's an actual inflection point because there's a change in concavity and this x value is in the domain of the original function. So let's go ahead and just look at an example with a simple polynomial function. Apply the second derivative test and find the inflection points and intervals of concavity for the function. Alright, so we go ahead and to get to the second derivative, we'd have to take the first derivative. So negative 15x to the fourth plus 15x squared. Want to go ahead and take the derivative again. So negative 60x cubed plus 30x. And I want to know where that is equal to 0 or undefined. There aren't any domain restrictions that we need to worry about with polynomial functions, so this isn't applicable for us right now. This is factorable. I can go ahead and take a negative 30x out of both terms. That leaves me with 2x squared minus 1 is equal to 0. Okay, if I want to go ahead and solve this, I could get a pips. My pips are going to be at x equals 0, and then x equals plus or minus the square root of 1/2. So just like with the first derivative test, we want to use a number line to try to organize our thoughts about concavity. So on a number line that I am now clearly labeling as a second derivative number line, your label is very important when you're showing work because otherwise a reader wouldn't know whether or not you're doing a first or second derivative test. So I want to, some changing points could be at negative square root of 1/2, 0 square root of 1/2. And these were all places where the second derivative was equal to 0. So I could plug test values in to the second derivative, perhaps using my calculator or by hand to come up with these values. But if I plug in a value that's less than negative square roots of 1/2, I end up getting the second derivative to be positive. When I plug in a value between the negative square roots of 1/2 and 0, I end up getting negative, positive, negative. Alright, so since all of these points are in the domain of the original function and there's a change in concavity here, change in concavity here, change in concavity here, these are all inflection points. So there's inflection points at plus or minus the square root of 1/2 and 0. This particular function is concave up from negative infinity to negative square root of 1/2. And then concave up from 0 to positive square roots of 1/2. Okay, it's concave down between negative square roots of 1/2 and 0. And then it's concave down after the square root of 1/2. So running a second derivative test is very similar to running a first derivative test. It's just the information that you're being told is about concavity rather than increasing or decreasing. Alright, so let's analyze the same function, but let's go ahead and look at the extrema and talk about how the second derivative could be helpful in this situation. So we had just taken the first derivative of this, and it was negative 15x to the fourth plus 15x squared. we won't care about where that's equal to 0. There's nowhere where it's undefined. So I can factor out a negative 15x squared, leaving me with an x squared plus 1. Oh, pardon me, minus 1. Okay, so my critical numbers are going to be at 0. And then from this factor right here, plus or minus 1. If we want to run a typical first derivative test, we'll go ahead and set up my number line, putting my critical numbers on there. Oops. And then after plugging in some test values into the first derivative, I ended up getting the first derivative be negative on this interval, positive on this interval, positive on this interval, and negative on this interval. So what that means is f would be decreasing and then increasing, increasing some more, and then decreasing. So then where are the relative extrema for this? So there will be a relative min at negative 1, and there will be a relative max at x equals 1. What's the second derivative at these values? So again, recall that our second derivative was negative 60x cubed plus 30x, and that we had that number line on the previous page, so we'll refer to that. But what was the second derivative at negative 1? What was the second derivative at 1? Was it positive or negative? Let's look at negative 1. So negative 1 would be in this interval here, and the second derivative was positive. If we go back and look at where 1 was at, so 1's over here. So the second derivative was negative. I can make a note of that. Let's see if that makes sense. We said that there was a relative minimum at x equals negative 1. Well, at a relative minimum, I would expect the function to be concave up. At a relative maximum, I would expect the function to be concave down. So I hope that these ideas go well together. In fact, the second derivative can be a good way to prove an extrema rather than talking about increasing or decreasing. So let's try to solidify some of these details. So what can you conclude about a function that has a domain of all real numbers at x equals a? So if f prime of a is equal to 0, so there's a critical number at a, and the second derivative is greater than 0 or positive, what can you conclude about the function? Well, if the function's concave up and there's a critical number there, I would say that there's probably that there is a relative minimum. Oop. Okay, if the first derivative at a is equal to 0 and the second derivative is less than 0, which would mean that the function's concave down, I would know that there's a relative maximum at x equals a. If the first derivative is equal to 0 and the second derivative is also equal to 0, I would know that neither is occurring, so neither a min or a max. But what could be happening is something that happens like on a simple cubic function. If we can look at this point right here, the first derivative is equal to 0 because there's a horizontal tangent, and the second derivative is equal to 0 because there's a change in concavity at this point. So there's the very typical behavior that you can use looking at critical numbers and concavity, and sometimes there might be a situation that requires more in-depth analysis. All right, so let's just practice again with another example. Apply the second derivative test to find the inflection points and intervals of concavity for the function. So let's already get going with the first derivative. So 4x cubed minus 4. go ahead and get 12x squared. We want to know where that's equal to 0 or undefined. A quadratic is defined for its whole domain, so that's not an issue. So it looks like I get my pip to be at x is equal to 0. I want to go ahead and run a second derivative test. If I plug in a negative number like -1, 12 times -1 squared is positive. If I plug in something bigger than 0 like 1, I also get a positive. So when I want to describe the function, I would say that the function is concave up on the interval of -infinity to 0 and from 0 to infinity, and that there was no change in concavity, even though there was some type of a break in the graph that caused this stop in the concavity, but there are no inflection points. Even when you're asked to please describe the inflection points, even if there aren't any, rather than leaving it off the list, please state that there are no inflection points. Okay, so this is a similar problem to what we've done before. It says sketch the first and second derivative of the function on the same axes. What we're going to do after we graph this, though, is to talk a little more in depth about what the second derivative graph looks like to the original function. Alright, so if I'm graphing the first derivative, I look at where there's horizontal tangents. There's a horizontal tangent here, so it's going to be a 0 on the first derivative. It's going to be a horizontal tangent there, so that's going to be a 0 on the first derivative. The function's increasing up to here, so I would expect the first derivative to be positive. It's also increasing at a decreasing rate, so that's how I know that it's up going like that. The function's decreasing from here to here, and then the function's increasing after that. So that's my first derivative. My second derivative, I can graph the derivative of the blue one. So the function's decreasing up until here, and then it's increasing after that. So something to note, though, is on the original function, the function's concave down up until, this point. And notice that the second derivative is below the x-axis there, noting that I would expect the function to be concave down. Similarly, after that point, the original function's concave up, and the second derivative is positive. So you have just some more information to help you better sketch graphs now that you know what a second derivative can tell you. So being able to analyze a function in an equation form is important. Being able to look at a picture of a graph and describe the function it's increasing and decreasing in concavity is important. But a table of values is another representation of functions you need to be familiar with. So I've provided some intervals and some values for a particular function, its first derivative and second derivative, focusing on the closed interval from 0 to 3. So assuming that f is continuous, what are the extrema on 0 to 3? So remember, extrema can be where the first derivative has critical numbers. So at 0, the function's undefined. At 1, the function's derivative is 0. And at 2, the function's derivative is undefined. So let's try to check out and see what's happening at these values. So from 0 to 1, the first derivative is negative, so that would mean the original function's decreasing. So if the function's decreasing and then decreasing, 1 isn't going to be a min or a max. But if it's decreasing from 1 to 2, and it looks like the original function would be increasing from 2 to 3, that there is a relative min at x equals 2. So we can make the conclusion that there is a relative minimum at x equals 2. Unfortunately, it wasn't particularly helpful at 2 to figure out concave up or concave down because the second derivative was undefined there as well. So perhaps we take a minute to figure out where the points of inflection are and then try to come up with a rough sketch of the graph just so that maybe puts it all into a little more context for you. So we're looking for points of inflection. So possible points of inflection are where the second derivative are equal to 0 or are undefined. So based on the table that we're given here, 0, the second derivative is not undefined. At 1, the second derivative is 0. And at 2, the second derivative is undefined. So at 0 is one of the endpoints of our interval, so that's not particularly helpful. But 1, is there a change in concavity? There most definitely is a change in concavity at 1. Is there a change in concavity at 2? No, there is not. So although 2 is a pip, it is not an actual inflection point. So at x equals 1 is the only inflection point for the function. Okay, well, what does this function look like? Let's try to come up with a rough sketch. So we're on the interval 0 to 3. F of 0 is 2. F of 1 is 0. F of 2 is negative 1. Okay, so if I try to figure out what's happening between 0 and 1, f is positive, f prime is negative, and f double prime is positive. So the function's decreasing and concave up. So try to make it as concave up as I can. Then after 1, between 1 and 2, the function's still decreasing, but now concave down. So try to make that look concave down. At 2, the second derivative and first derivative are undefined. Since the function's continuous, this will be a cusp. And then after that, the function's increasing and concave down. So I just kind of have it going something about like that. And I don't really know what it's doing after 3. I probably should just stop my graph at 3, but this just kind of gives you a rough idea of what this function potentially could look like. So in this lesson, we've talked about what a second derivative can tell you about a function, that when the second derivative is positive, the function's concave up. When the second derivative is negative, the function's concave down. And to use this to help describe what the function looks like better, and also as a tool to help you decide if there's a relative min or max at a particular value.